In any case, there's a handout today. Hopefully you guys all got it. And we're going to be doing trees. And as a few people have observed, hey, we did some of this before. And I did actually just copy some of the procedures from before. But there are many, many more exciting procedures on trees that we're going to do today. Yay. So, trees. So, to just sort of refresh our memory, trees. Let's say we had something like this. I can have a 5 up there. Okay, so here's a tree. Trees don't have to be binary trees. How would we represent this tree in Lisp? Yeah. Okay, so the way we can look at this diagram is this here is a 3-element list. First element is 1. Last element is 5. The second element points to a 2-element list. In this 2-element list, the first element is 2, and the second element is another 2-element list. 3, 4.
So your midmost list should be 3.4?
No, why would it be 3.4?
Oh, I'm sorry. Oh, sorry. Can you distinguish a pair from a list?
Well, it depends on how you decide to represent a tree.
Yeah.
We're representing a tree by using lists. We're not using const cells. Now, we could try to, if we had a binary tree, it wouldn't work with a 3-element tree. But let's say we did have a binary tree. Maybe I should put a few less layers in here. Okay. So then we could represent this as const cells if we wished, where the car points to the left side of the tree and the could point to the right side of the tree. So this would be an alternative representation for trees. Okay. Now, if we represent them as const cells instead of lists, we lose sort of the nice property of being able to cutter down the list looking for nils. So what we're going to have to do, if we're in this sort of representation, is we're going to need to check if our second pointer is a pair or if it's a single element, similarly with the car pointer. So we're going to just need to check things. Instead of being able to say null, check for the end of the list, we'll need to check to see if we've got a pair or an element on each element of the tree. So it's a different representation. We have to do things differently. Now, if we were to do 2 different representations, what would be a nice thing to do so that the user wouldn't see this? And we could build some sort of data abstraction where we map something into the left child and the right child, and it would depend on how we look at it, and then we would have some test for no more tree. But there is a key difference between this tree here and that one, and that this one doesn't have to be a binary tree. Okay, so these aren't exactly the same. So today we're going to be looking at these non-binary trees, and we're going to leave that cons representation for you guys if you want to go off and play with it. Because I know you guys have lots and lots and lots of free time. Okay, so let's see. Page 1 has a couple of trees defined, count leaves, which we did, fringe, which we did. I do not believe that we did some fringe. Is that correct? We did not. Nobody remembers, so we'll do it again. Let's write a procedure, some fringe, on a tree. So what I want this procedure to do is to add up the leaves of the tree. So it'll return 1 plus 2 plus 3 plus 4 plus 5. If you recall, fringe returned the list 1, 2, 3, 4, 5. Sum fringe is going to add the result of adding those. That's fringe. That's sum fringe. Isn't that sum fringe? Okay. I'm just kidding. Okay, first thing we check. Do we have a null tree? If we do have a null tree, what in this case should be our base case? 0. Right, we're adding. Next case, what do we want to check for? If it's not a pair, right? To make sure, to see if we have a single element. And if we have a single element, what do we want to return? That element. Okay. Now what do we want to do? All right, we need to sum fringe on the car and the cutter. We probably want to do something to combine them. I'm going to add the sum fringe on the car of the tree and the sum fringe on the cutter of the tree. Okay. Now, assuming that we had just looked at fringe, which is on your sheet, we haven't written on the board, and sum fringe, there's some pattern in these. Because scheme is all about capturing patterns, let's write accumulate tree. Okay. Let's think about what's the pattern that we can capture and what's going to change. So let's look at sum fringe as an example. What are the pieces here that you think are going to change from each procedure? The null value. Right. Some sort of a term procedure. Okay, so we need a term, a combiner, a null value, and hopefully a tree. So have a tree. Make sure I get the parameters in the right order. Term, combiner, and a null value. What's this procedure going to look like? Am I still going to have this cond? Basically, anything that I didn't circle or square off right here is going to stay the same. Obviously, we'll change this name. So, cond, null tree. We have a null tree, null value. Okay. If we don't have a pair, meaning that we have a single element of our tree, what would we like to do? Term to the tree. Otherwise, of what? Accumulate tree on the car. Can I just close there? I gotta send all the other stuff. Term, combiner, null value. One. With an accumulate tree on the cutter of the tree, also passing term, combiner, and the null value. Okay, given accumulate tree, tell me how I can write some fringe in terms of accumulate. Right here, well, we need to call it so we're going to accumulate tree. On the tree, the term is what? Identity, which we write as, okay, there's our term procedure. What's going to be our combiner? Plus. And our null value? Good. What if I want to multiply the fringe? It's going to look pretty much the same. Still going to have the same term procedure. Good. Okay, so what if we want to count the leaves of the tree? I want to know how many leaves there are in the tree.
Just out of curiosity, what would happen if instead of our term being the lambda x, we call it the term car?
So question is, what if we passed as term car? Well, if we get here, and our term is car here, and we say car of tree, but we don't have a pair, what's going to happen? They have a popular boom. We're going to get an error because we don't have a pair, and we can't apply car to something that isn't a pair. So we'll get an error there. So we can't use car as our term. Because when we're using term, we know that we don't have a pair. So you wouldn't want to pass car, could, or any mix of them as your term.
Is not pair basically atom?
Atom doesn't exist in our version of C. You could define, sure. You could define atom of X to be not pair X. Okay, and some scheme books will use atom. I believe the first edition of this book actually uses atom.
And there really is no difference between a pair and a list. I mean, pair question mark is almost like the same list question mark.
Pair question mark is just checking to see if we have some sort of box and pointer structure. So a list is going to be null terminated.
Oh,
So pair isn't telling us anything about whether we have something that's nil terminated with a nil. All it's telling us is some box and pointer structure.
so 4.3 is not considered a list. That's
Right. So that's actually a cons cell. That's cons 4.3. That's not a list. It is a pair, but it's not a list. Okay? Okay, we want to count the leaves of a tree. What? Lambda x1. So we just want to count each leaf. Cool.
Is the term only applied when you're down to a single?
Right, term is over here. The only time term is used is when we're down to a single element.
Okay.
So what we need for term is we need a procedure that takes in one argument and does something to it. Can return 1, 0, the identity, depending on what we want to do. And actually we'll see a case right here. Let's write fringe, which if you look at page 1, you can recall the definition from a few classes ago. Let's write fringe in terms of accumulate tree. Okay, so what's the term procedure here? List. So, say, do I have to do that? Could I just say list? It would make, so what I'm asking is, instead of passing this procedure, could I just pass it like that? Well, term, we would substitute in the list procedure, and list could actually be applied to tree, and it would actually work just fine. So either of those would work fine. Questions on that one? It's just like we passed plus here before, instead of passing in lambda xy plus xy.
How does it work if it's not a two-argument combiner? Like, what does list do?
Arguments. Let's say we only had one. Well, that's equivalent to cons 1 onto nil. And if we have list 1, 2, well, that's cons 1 onto the cons 2 of nil. Okay. So list can take any number of arguments. So we can actually use list here, or we could use list as our combiner without having to wrap a lambda around it. Just like we could do the same thing with plus or times. We don't have to have it take a specific number of arguments. The procedure itself can do that.
With that representation, is there an extra step involved with the lambda instead of using this? I mean, I know it's very little, but there is an extra step.
Right, because the lambda creates a procedure object and then it's applied. Whereas this, it'll just look it up and apply the procedure. So we're not actually creating an extra procedure object. Okay, so that's our term. What's going to be our combiner? Append. Which I can write that way, or I could write lambda xy, append xy. Either way. Finally, what's going to be my null value? Empty list. No. Okay. So our terms, our combiners, doesn't need to be just something on arithmetic. We could have list operators as combiners.
Why could this not have been written with the term being lambda xx and the combiner being cons?
Okay, let's actually write that, and let's see what happens if we do it that way. Let's define, I'm going to call this copy for maybe some reason. And let's accumulate the tree. And what we're going to do is pass a tree. You wanted the identity element. And then cons, right? And then nil. Let's follow this through. Let's find some board space to follow through on. Let's keep accumulate tree since we're currently using it. All right, so we're going to copy a tree. So let's copy something small and happy. 1, 2. So copy 1, 2 sets off a call to accumulate tree, which I will abbreviate as A-T, of the tree, our list 1, 2, our term procedure, lambda x, x, our combiner, list, cons, sorry. Nil value. Okay, what happens? Got the call. Is our list null? Is it not a pair? It is a pair, therefore not a pair is false. So we come in here, and we call combiner cons on accumulate tree of the car of the tree, which is the list one. And then, if you guys wouldn't mind, because it's going to be the same every time. And we're going to cons that to accumulate tree of the Kutter, which is it just 2? So list 2.
Right.
There's our list. The car of the list, what's pointed to here? That's the list 1. The Kutter list, what's pointed to here? That's the list 2. Okay. So now, cons accumulate tree on the list 1 fall here. So we're going to cons 2 things together. Accumulate tree on the car, which is to the accumulate tree of nil. The Kutter of this, so the car, this is what we're looking at right now. The car points to 1, and the Kutter is nil. Okay. So, and then we have, well, let's finish up this call first. Accumulate tree 1, not null, but this becomes true. Term of the tree is 1. Okay, now we're going to accumulate tree on the nil. Well, that's null, and we return the null value, which is. Okay, so here we've got cons 1 nil. Now let's go off and look at accumulate tree on the list 2. Well, that's not null. It is a pair, so we fall through to here. And we're going to cons accumulate tree on the car, which is, what's the car of the list 2? To the accumulate tree of the Kutter, which is, okay, so accumulate tree on 2, term tree, which is, then this goes through, it's the null value, nil. So here we got cons 2 nil. Okay, so I'm going to cons 2 things together. Cons 1 nil, well, what does that give me? The list 1. And cons 2 nil gives me the list 2. What happens when I cons these 2 things together? Well, actually, let's just draw the box and pointer diagram. See what happens. So I've got the list 1 and conveniently drawn the list 2. I'm going to cons these 2 things together. I build a con cell. It's the car. That's the Kutter. Does this look familiar at all? We've rebuilt the exact same structure. Okay. Now, why would we possibly want to build the same structure again? Because we might want a copy of it. If we make a copy of our tree, so this is our copy. So let's say we define this to be C. So this is going to be C pointing here. And let's say that we had defined this tree here to be something like A. If I ask EQAC, what will be returned? False. How about if I ask EQV on A and C? Still false, because remember, EQV is going to use EQ when it's testing out pairs. How about equal? That is going to be true. Okay. So, we haven't talked about mutation. We will next week. But we're going to find that we have ways to go in and destructively modify lists. So, what we might want to do is if we're going to destructively modify a list, make a copy of it first. So then we'd have a copy of the original list, and then we could modify our changed copy. But we'll see that next week when we start talking about mutation. Other questions? Sure. Right, because
These just replace the old. These do everything that you
right, because a tree doesn't need to have multiple structures in it. So this could be the same as the old ones. Sure.
But it's less efficient on flat lists than the ones we wrote specifically to deal with flat lists, because we're calling the functions.
So the question is efficiency, and in fact, we are making one extra call here, right? Because in a flat list, we would assume here that we could do something straight away to the car of the tree. Okay, so it's a little different in the way we've written the code, and we would make an extra call to the function. But it's going to function and act the same way. Other questions? Okay. Let's look at map tree. Do you guys recall map from lists? Okay, let's write map for trees. Okay, so the difference is going to be that if you applied map only, let's say we just applied map to a tree that had some depth like this. Am I going to run into trouble with it? Well, what map is trying to do is just trying to apply the procedure to the car. When I get to the car here, is it a single element? Can I apply something to it? I might run into some trouble if I'm trying to just add, because I can't add a con cell. So let's write map for trees. Okay, so map tree, and which way did I? An operator to a tree. Okay, so what do we want to do here? I guess we could accumulate tree, sure. Wasn't the way I was going to write it, but sure. Okay. What's my term? Okay, here, lambda x, op x, or here also op. Okay, so either of those is going to work. So that's how I get my term. What's my combiner going to be? Cons. Because I don't want to change the list structure at all. I'd like an identical list structure, so I'll just use cons. And my null value will be there you go. Now we have map tree. If you'd like to see the alternative way to write map tree, you can look at your handout, the top of page 3. I could rewrite it here if you'd like. This is another way we could write map tree. Slightly less elegant. We check if the tree is null, nil, not pair, tree, op tree, else, cons, map tree, op, car tree, to the map tree, op, critter tree. That's conned, not and, by the way. Different way to write it. Okay, once I have map tree, of course we're going to want to use it. So what if I want to write a procedure called scale tree? And I'm going to scale a tree by some factor. What would I write here? Map tree. No, we want the tree first. Sorry, op first. Sorry, yep. Lambda. Okay, and now the tree. Okay, so if I wanted, let's say I have a tree called tree 1 defined, how would I scale my tree by 10? I'll scale tree 1, 10.
But the above sentence with 10 as factor.
Hmm?
The above sentence with 10 as factor.
I'm sorry, actually I didn't hear it either. So the above procedure with 10 passed in as factor? Yes. Right, it's a call to the above with 10 as a factor. Okay, and that's going to preserve the list structure. It's just going to scale every element of the tree. What if I wanted to let's see. Maybe I want to write something where I zero out the elements of the tree. So I preserve the tree structure, but I change all the elements to 0. So,
Lambda x would just be
yeah.
do lambda x is 0.
So 0 tree could be defined to be scale tree. Need to pass a tree. Need to pass it a tree. There you go.
Would you even define it as a separate procedure, or would you just call scale?
It depends. It depends on how you wanted to use it. Let's say we wanted to use this a lot, and if we wanted to zero out a tree to reinitialize our tree for some reason, we'd probably want to call 0 tree. It would make our code easier to read, whereas if we called scale tree, tree, and 0, it's not quite as obvious from the name what's happening there. So we could redefine it. We wouldn't need to, but it would make it a little bit clearer to read it that way. Okay. How about...
What would happen if you didn't have parentheses around 0 tree tree and got rid of the call of the tree? I mean, would that just, when you just pass in the 3 and the scale tree, the tree and the scale tree?
define 0 tree to be what?
Well, you had it, except you don't have it as a procedure. It's just the tree would go into scale tree as opposed to.
This? How do I get the tree here? So what? So I could define something that wraps it. So I could say lambda tree, scale tree, tree 0. Is that any different than actually writing it this way? It's a desugared version, right? So either one of those is going to be fine. Okay, we could also write this a different way. We could define 0 tree of a tree. Well, we could just do a map tree where we have lambda x 0 on the tree. Same thing, different ways to write it. Yep.
What if you had a tree full of symbols as opposed to a tree full of numbers, and you wanted to clear all of them out, either replace them all with nils or replace them all with just a sort of like base kind of identity symbol?
You just replace the
Second
0
one before doing that.
So we could define replace symbol tree with some symbol. Okay, and here we would do map tree lambda x symbol tree. Okay, so I would replace everything in the tree with some symbol that we wanted to use.
Some of our map trees, the one in the handout asks, is it a number? Only trying to apply an operator to a number. So
Right.
we need the more general purpose map.
For question mark. And in that case, we would have trouble if we had a symbol. This is the better version. It would be better to write it. Well, we could define map tree number where we check to make sure we have numbers. But this would be the more generalized version of map tree.
Number means that it's both a number and not a pair?
Number question mark. Right, if it returns true, if it says it's a number, we know it's not a pair.
Okay.
Couldn't you just redefine map tree, accumulate tree to pass in a Boolean test as an argument, so that you just created one more variable now, and now you have a way of choosing what kind of test you want to perform on the other one?
Well, we don't actually need to write any accumulate tree. Term could actually be a lambda that had some sort of test within it.
Oh.
Right? So our term, we could write something like lambda x, then we could say cond number x, and if we have a number, then whatever, we want to do something to it. Otherwise, if it's a symbol, do something else.
So now it's just here. I do know.
Actually, let's not do symbol. This is not a number. We can just say else. Now is that just as good? Well, I mean, this is a little bit messier to have to pass in that sort of a term procedure. It's not really neat. It's not really very elegant.
You could write filters for them,
We could certainly write filters, right?
but that's where you put it in.
Right, and then we could filter out anything that wasn't a number and then pass it over and do all sorts of things like that. But with the rest of class today, and maybe we won't need the rest of class in this, in which case we'll come back and look at some other procedures. I want to look at actually depth first, but rather breadth first search of a tree. This is a question I got from Baruch at the end of the class last time we did trees. How could we go through a tree and print it out in breadth first order instead of depth first? Or 5, it'd be better if I drew this a little bit lower. 6. Everything that we've been doing so far would be a depth first traversal. And what that means is we go to the left branch and we go down as far as we can till we hit the leaf. Well, in this case, it's just a 1. Then we go back to the main node, go down the next branch and follow the left one down as far as we can. Go back up to the node, follow the next branch, go back up to the top, down the next branch, off to the left, back up to the right, back up to the end. Okay, so that's going to be a depth first traversal. We start on the leftmost branch, go as far down as we can, and then we backtrack to each node and go down the right children of that branch. A breadth first traversal well, in this case, what we do for breadth first is we want to look at this level first, and then we want to look at that level second, that level third, and if there were any other levels, continue going down. So in this case, if we did a breadth first visitation of the leaves, we would get a 1. These are not leaves. Then we have 2, 3, 6, followed by 4, 5. So let me draw this as a list structure so we can see about how we're going to attack this problem. The topmost list is a list of 3 elements, with the first one being 1, with the second one being a list of 2 elements, and that list has a 2 as its first element and a 3 as its second. And then the third element, well, that's a list of 2 elements. And that list of 2 elements has, as its first element, another list of 2 elements. And then the 6 over here. You guys feeling comfortable with box and pointer diagrams? Okay. This is the way that we envision when we do list structure. This is the way we start looking at stuff. Okay, so what I want to do for a breadth first traversal, when I draw it this way, I can say, well, I want to look at this list structure first, this level of list structure. That's my first. Then, this is going to be my second level of list structure. And that's going to be my third, et cetera, et cetera, et cetera. Okay. So given that list structure, let's not start writing code. Let's talk about how the heck we're going to do this. How are we going to think about traversing the tree? So far, we've just been cootering down it. But we can't do that. We can't just go off and take the car and do all the stuff we want to do on the car. So what we really want to do is we want to walk across these elements first. And then we want to get down to these elements. Okay. So how could we do that? Okay, we can check if the car is a pair or a number. Or we could, to be more general, say an atom, if it's a pair or not. Because we may have lists of symbols that we want to traverse in breadth first order. Okay. So we want to check to see if the car is a pair or not. Well, in this case, the car is not a pair. What do we want to do if it's not a pair? We're going to add it to our list. Okay. If it is a pair, what do I want to do? So in the case here, where I've got a pair, what would I like to do with it? I want to leave it alone, right? I don't want to do it right now, but I want to come back to it. So we're going to have some procedure, breadth first, that's getting past a tree. So I somehow need to remember that I want to go back to that tree because I don't have an extra variable. Well, if it's a pair, what I could do is I could take that structure, the car of my list, and I could bring it up here. Right?
So you append it after the null?
I could append this tree to this subtree. And this is going to have the nice property when we do this append of taking away one level of the list structure. Okay. So then we basically promoted it up here in our list and taken out one level of the list structure.
Doesn't append work the other way?
No, what append does is it cooters down each of the lists in the first, and then it just basically, the last cons, it conses onto that list. So it'll have the list 2, 3, and we'll just cons to it. So append. Should I rewrite append for you guys? No. Append takes list 1 and list 2. It cooters down list 1, building up a structure of basically the car, of list 1 with the cons of the catter of list 1 till the point where we hit nil on list 1, and that final cons has list 2. Okay, so the append's basically cuttering down the first list and then sticking it with the cons to that second list in the append. Okay? Yes?
What happens to the cell that was pointing to the 2, 3 originally? Is it still there?
Well, what's happening is we're starting to cutter down the list. When we got to this point, this would have been our tree here, actually, right? We would have been looking at that. And what we're going to do is we're going to say, I'm going to take the cutter of the tree that I'm currently looking at, in this case will be this, which had the nil, and append that to this moved up. Yep. So now when we get here, the car is this list structure. I'm going to take the car, this is messy, append it there, and continue going down my list. Let's write some code and then look at how the code's running. So let's define breadth first of a tree. Okay. So I have a tree, and we've been talking about what we're going to do if we have a pair or not a pair. But what should we do first with the tree? Make sure it's not null. If it is null, what should we return? Okay. Second, not pair tree. So if we don't have a pair, well, we talked about how we're breaking this down. Did we talk about how we were building it back up? Are we going to use cons to append, or are we going to use cons to build it back up, or append to build it back up? Right. We're going to use append because this is what we want to return. We want to dump all that internal list structure. Make it all go away. So if we're going to be using append, then we want to return the list of our element. Else, we've just been saying we're going to use append. Okay, what are we appending? Actually, have we finished yet? That's not right. Car pair. Because if we know if we've gotten to this part of our cond that we can safely take the car of the tree, right? Because I've just made sure that tree is a pair by that step above. So if I get here, I know that I can safely take the car of the tree, and I'm checking to see if it is a pair. If it is a pair, what do I want to do? Well, we need a recursive call. But first we need to somehow leave something behind to build up our list structure, right? All right, so we're going to Okay, scratch about leaving stuff behind. Do we need to leave stuff behind right now? If I've got a pair in my car, am I appending anything right now to my answer? No, right? There's nothing for my answer yet because I don't have an individual element. All I want to do is put that off to do it later. So we're going to just make a recursive call to breadth first because we have nothing to append here. There's nothing that we need to delay to build the list back up because we don't have an element to put on the list. Okay, so our recursive call will be breadth first applied to what? Append of Cooter. I hear Cooter and car. Cooter. Take the Cooter of our tree. So in this case over here, we were talking about this case. So this is the car of the tree that we just checked. This is the Cooter of the tree. We're going to take the remaining list here, and we're going to append it to the car of the tree. Questions? Otherwise,
Don't we want to cons the car of the tree onto the cutter of the tree?
I'm going to append it because I want to flatten my list.
But won't that reverse it? That'll put it in the back.
No, append is no reversing. So all append does is it cooters down the first list, keeping it in the same order, and then sticks it onto the second list.
But we don't need to flatten it if it's not a pair.
It's down the first list and it sticks the second list on the end of it, though.
If the car of the tree is not a pair, why do we need to flatten it? It's already flat.
Well, we saw with copy that in some cases where we do get down to a non-pair, we still need to use append. But here's a cool thing. If we're using the append on our tree and we're bringing our tree up like this, are we going to actually have anything left to flatten at this point?
No.
So we can actually cons. Yeah.
Cons the car of just the tree on
In the tree.
Just the
All right. I actually wrote this on the handout with append. So now we're going to cons what to what?
carve the tree onto the cutter of the tree.
Am I going to hit that not pair case very often at the top? Depends on what the tree looks like. But for the most part, right here is where we're taking care of those single elements. Right? We're actually not recursing on the car of the tree. We're just consing it on here. Yes?
Is there any way, I don't know if you have time, stepping through briefly?
Yeah, let's go through it. Let's clean everything up and do it. Okay, we want something with depth, but that isn't too long. So let's do 1, 2. I'd rather.
The one in the handout is the list 1, 2, and then 3, 4. Okay.
I'd rather have it be in the.
List 1, 2.
I'd rather have, yeah. What should this return?
1, 4, 2, 3.
1, 4, 2, 3. Okay, so let's do it. Is the tree null?
No.
Is the tree not a pair? Is the car of the tree a pair? Would this help if I drew out the list? Let's draw out the list. There's our list. Top level is 3 elements. 1, 2, 3. And the second level has those 2 elements in it. Okay, so is our tree not a pair? No, it is a pair. Is the car of our tree a pair? No. So we're going to cons 1 to the result of calling breadth first on the cooter of our tree. Our tree is now that. It's easier for me to write the numbers in the substitution stuff. So, cons 1 to the breadth first of this list. List null?
No.
It is not a pair. Well, yeah, it is a pair. So, is the car a pair?
Yes.
Yes. So, I'm going to call breadth first on append the cooter of the tree, which is the list 4. This is the cooter of the tree here, to what? Car of the tree. This is the car of the tree. Okay. Now, I'm going to append the list 4 to this. What this will come down to once we make the calls to append is we'll be consing 4 onto this list 2, 3. Which means our structure is now going to look like this. This is gone. We're going to take 4 and cons it to that. This I'm going to erase right now. Scheme would keep it around. We would need to do something to get rid of it called garbage collection, which we will see at the very end of this course. But let me just do it myself and erase it. Now I have the list 4, 2, 3 being passed to breadth first. Okay, so this becomes cons 1, breadth first, 4, 2, 3. Questions so far? Okay. Breadth first, 4, 2, 3. Nil? Not a pair?
No.
Car a pair?
No.
Okay. Otherwise, we're going to cons the car of the tree, 4, to the result of calling breadth first on the cooter of the tree, the list 2, 3. This is now our tree. Okay, breadth first 2, 3. Not null. Not an atom. Car is not a pair. So now we have cons 1, cons 4, 2, some number of parens. Okay, is it BF3 or is it BF list 3, right? Because we're taking the cooter. That is now our list. Cons 1, cons 4, cons 2. Okay, BF on the list 3, not null. It is a pair. The car is not a pair, so we fall through to our else case, and we will cons the car 3 to the cooter, BF on the cooter. Okay. Cons 1, cons 4, cons 2, cons 3, BF nil, returns nil, finally. and this starts collapsing. So this makes the list 3. And then we're consing 2 to it, which gives us the list 2, 3. And then we're consing 4 to that, which gives us a list 4, 2, 3. And then we're consing 1 to that, finally giving us the list 1, 4, 2, 3. Is this what we expected? Yes. Yay, we're happy.
We did that entire thing without using the second rule.
Yeah.
Do we need the second one, or is it just this tree?
Okay. Do we really need the second rule? Are we actually going to hit a case where we hit that second rule?
Unless you don't give it a
It's a
tree.
well-formed tree.
If it's a well-formed tree, we shouldn't hit that, right?
Which rule are we talking?
This one here. Do we need this? It gives us a nice error check, right? Because here we're going to go try to take the car of the tree. And it gives us a nice little error check to make sure that we can get the car of the tree. But because we never recurse on any of the single elements, we're passing the list down, we shouldn't actually hit that case. So we could take it out and try things out and see if it works okay.
I just did. It works on all the lists that we
Huh?
I just tried it. It works on all the lists that we fed it. But it would work if you fed it a single number.
It's not going to work if you feed it a single number. But one could argue that a single number is not a tree. But in fact, a single number could be a tree, right? Because that could just be the tree with a node 3. I mean, I guess we could just draw this. That we could just say 3 is a tree. It depends on how we define our trees.
Tree's a number. There's no pointer.
Yeah.
What you've drawn on the left is a list. What you've drawn on the left is a list.
Right.
But
Right.
it doesn't, I mean, I guess it's a trade-off again. I mean, it's computationally really not, it's not taxing us very much, but should something get in there, we'd be really happy it was there. Right?
Are we error checking? Is it worth the error checking?
I guess it depends on
It depends on, it really depends on how we define a tree and how a user thinks a tree can be. And if a user thinks a number can be a tree, like this, as opposed to this, then we should have that there.
Couldn't you just, I mean, if you wanted that kind of error check, put that on top of a function that's inside, so you just check the tree when it goes in, and then just recurse on a loop that's inside, on a function that's inside.
Sure, we could do that. We could have an additional loop that when it's passed in, we could say, is it a number? If it's not, then we'll call the helper function and start running off on it. We could do it that way too. So this case is probably not going to be used. Be taken care of by everything else. Questions on searching this way? Or printing elements out this way? When would we use breadth first search? What a good question. Anybody have any ideas?
Depends on what your tree is representing.
It depends on what our tree is representing.
If it's representing a family tree, you might want to print it out by generations rather than by...
Right. So let's say we had a family tree represented by our tree. We might want to say, who are all the children of the main node? So, we have, your great-grandparents, and who are the children of your great-grandparents? And you'd like to find out who their grandchildren were, and finally who their great-grandchildren were, and maybe great-great-grandchildren, depending on how far back it goes. This would be one case where we want to do breadth first search.
Well, wouldn't this kind of apply to the problem set too? Like looking at prereqs, I mean, you look at this layer, then you want to look at the layer beneath that.
Breadth first search would give you the order you needed to take on it.
If you built the tree up where you had everything going back, then you could get it in the order you would need to take them. Sure, it could apply to this. You may not need to do it in breadth first search, but this might apply to the problem set, yeah. The other thing this tree might be is, let's say we had some sort of a representation for a game of chess or something, and we build out some tree, and every leaf turns out to be a move where we end up winning. we may want to find out the shortest number of moves to somewhere where we win. So we'd search the breadth first to see the shortest number of moves it would take us to win the game from that point. So that might be something. So basically what you're going to do is you're just going to keep doing a breadth first search across all these moves until you hit a leaf. And when you find that leaf through the search, then you would say that would be the shortest number of moves it's going to take for me to win the game. Yes?
Or similarly, if it's computationally intractable to do a depth first search, you may want to do just breadth first as you go along.
Right. You can do it as you go along. So maybe you don't actually want to enumerate every possible chess move. Right? You guys heard of Deep Blue? IBM? Chess playing computer? So part of their win was that they had lots of processors and they could look ahead more steps. So they had a deeper search. But they couldn't still enumerate a full game. Right? So that's part of what's going on. So if you couldn't enumerate the full thing, you might go to some maybe strategic advantage point. So rather than marking a leaf as, I want to find a leaf where I win, you could say, I want to find a leaf where I consider myself to be in a better strategy, or a better, not a real chess player, as you can probably tell, but I'm in a better board, whatever it is, position as opposed to my opponent. Okay, so that's one other thing that you could be looking for with the depth first search.
Could you give a real life example of when you might want to flatten a tree or flatten top level like we had in your code?
Our homework assignment.
Yeah, you might want to flatten things in your homework assignment. If you get lists of lists, maybe. Or, although flatten is different than fringe. Okay, just to point that out. Fringe is sometimes called deep flatten. So there's flatten and there's fringe, sometimes known as deep flatten. And this is going to remove one layer of the list structure. So let's say we did a flatten on the list 1, 2, 3, 4. Well, what flatten would return is the list 1, 2, and then the list 3, 4. Okay, so it's not going to flatten everything out. It'll flatten that top layer, one layer only. Fringe, if we applied fringe to the same list, you'll notice that my trees are usually conveniently ordered. It would return the list 1, 2, 3, 4. So that would take an additional list structure if we had it. So that's the difference between the two. Which is why sometimes it's called a deep flatten, because it will recurse and continue to take out the list structure, whereas flatten will only do one level of it. Other questions? That's all I have for today.